All right, so let's go back for a second to a positive and negative charge. What exists between the positive and negative charge? A force of attraction, right? This guy's experiencing an electric force this way. This guy's experiencing an electric force this way, which is defined by Coulomb's law. And since they're of opposite charges, Q1 times Q2 is negative, therefore the force is negative, and so we call that attractive. Good. Now, what if no, F of E for both of them. Electric force for both of them. Yeah. What if there's just one charge? Is it exerting a force on anybody? No. But is it doing anything to the area around it? Yes. Yes. It's creating what we call an electric field.
Is that like a force field?
It is a type of force field, yes.
Are those like real force fields?
Okay. So now, what I mean by that is that it's creating a field so that if I bring a charged particle into that field, that charged particle will experience an electric. What were we just talking about here? Force, right? If I put a charge right there at point P, it will experience an electric force because of the electric field being caused by this positive charge. And so to describe that electric field, we're going to use what are called electric field lines. And field lines are defined by the direction of the force. I could even say the net force on a positive test charge. So for example, with this single positive charge here, is there a field at point P? Yes. What is the direction of the field at point P? Up, down, left, or right? Right. Because if point P had a positive charge, it would be pushed to the right. So I can draw a field line directed to the right. Easier. Yes. We actually call it an electric field map, if you. Yeah, it starts off fun, right? What about at this point here? Yeah. It's all fun and games till you break the calculus out. What about this? What's the direction of the field at this point? Down.
Is it still P?
P was just an arbitrary point.
Oh, okay.
What about, because if I were a positive charge and I was here, which direction would I be pushed by that positive charge? If I was here, I would be down, right? And what if I'm here, which way do I get pushed by that positive charge?
Left.
Left.
What if you're like in the middle? You get pushed.
What if I'm right here?
Okay, so it's like a diagonal one?
And if I'm here? So as you can see, electric field lines, because they show the direction of a positive charge, they always go away from positive charges.
They always do?
Yes, ma'am. And I can demonstrate that also or the opposite of that, by doing a field map for a negative charge. What's the direction of the field at this point? Down, because if I were a positive charge, I would want to go towards that negative, right? And if I were here, so field lines always go away from positives and toward negatives. Right? That's the first of our 4 conventions related to field lines. And by convention, I don't mean something you attend. I mean agreed upon set of rules. The first convention is that field lines go from positives and to negatives. Second convention is that the density of the lines indicate the field strength or the magnitude of the field. What do I mean by that? If I draw a square of that size, and then I draw a same size square farther away from that negative charge, what's true about the density of the field lines in square A and square B? Yeah, the field lines are more dense in A than they are in B. That's because the electric field is stronger at A than it is at B. And that makes sense to me because why? Exactly. The smaller the radial distance, the closer I am to the charge, the what? The stronger the force, and therefore the larger the field. Right? Third convention. I'm going to draw another diagram to illustrate the third convention. Let's say I have a positive 4 Coulomb charge on one, and on each side of it I have negative 2 Coulomb charges. Well, first of all, what would the direction of the field be between these two guys? To the right, because it's going to go away from the positive and towards the negative. What about between these two? Which way? Left, because it's going away from positive onto negative. And then there might be another line that goes this way, and this one. Right?
But there's no point, it's just line.
Right. I mean, there's points in just the sense of the definition of a line, that it's an infinite set of points. So if I pick a point, right, just any arbitrary point right here, which direction will a positive charge be pushed? Well, right there, along that line. Right. All right, so the third convention says that the number of lines terminating on a charge is proportional to the magnitude of the charge. Well, what do I mean by that? In this case, the positive charge is a 4 coulomb charge, whereas the negative charge is a 2 coulomb charge. So how many lines should be terminating on the 4 coulomb charge as opposed to the 2 coulomb charge? Twice as many. And let's see if we've drawn it correctly. There's 1, 2, 3, 4, 5, 6 on the 4 coulomb, 1, 2, 3 on the 2 coulomb. Is that correct? Yes. What about the 2 coulomb and the other 2 coulomb?
So it doesn't have any kind of balance.
Has to be proportional. So if they have the same charge, right, the 2 coulomb charges have to both have the same number terminating on them, which in this case is 3 and 3. So what's wrong with this field diagram?
The left side has more than the right side.
Okay, good. This 2 coulomb charge has 4 on it, and this 2 coulomb charge only has 3.
Okay, so why is it giving you 6 if there's 4 coulombs?
Well, there doesn't have to be 6, but there has to be twice as many as there are on the 2. So I can easily fix that by doing this. Now is it fixed? Yes, because now on the 4 coulomb I have 1, 2, 3, 4, 5, 6, 7, 8, and on each of the 2 coulombs I have 4. So are they proportional to the charges? Yes. All right? And that makes sense following from number 2, right? If the density of the field lines indicates the magnitude of the field, if I have twice the charge, then the field's going to be twice as strong, so there should be twice as many field lines on that charge. All right, then finally, the 4th convention is this. Field lines can never cross. They can't intersect. In other words, for example, I can't have a field line like that. This one right here. Actually, let's change its color. That's not legal. Why? But why? Why can't they cross?
Because their charges are
But why is it the convention? Why can they not cross? What did we say lines are defined by? But field lines. What are field lines defined by? Good. The direction of positive test charge is going to experience a net force. If I put a positive test charge right here, what's the direction of the net force? Is it here? Or is it there? You don't know. Is it possible for there to be 2 different directions that a net force can be pointing? No. So since there can't be 2 options for the same test charge, there can never be an intersection of field lines. Since there can never be 2 directions for a net force for one test charge, there can never be an intersection of field lines, because that would mean there's 2 choices of the direction that positive charge could be pushed. All right? Questions? All right, let me show you this real quick then.
You put all this on online, right?
Yes.
Somebody can watch it.
Yes. Oh, come on. All right, so first of all, what just happened? Yeah, she started filling up her tank and got back in the car. Now, have you noticed the warning signs that tell you now to not re-enter your car when refueling your tank? Yes. Those are new. There are, if you read, there's warning signs now that say not to do that. This is why. First of all, what is she wearing? Jeans and, a sweater, which means there's probably a lot of static in the sweater, and it's probably cold air, which means there's less moisture in the air, less humidity to draw the static off. And so there's going to be a buildup of static charge. Plus, by getting in the car, she's going to rub against the car seat. And then what's she doing there? Yeah, she's tugging on her sweater, again, causing more buildup of charge by conduction, so that there's a buildup of charge on her body. Now, if she were smart, if she had taken physics, what should she do right now? Touch the car, right? Or anything else metal, so that she can ground herself. Allow those electrons to then jump off onto the metal surface. But the first metal thing she's going to touch is right here, which is right near where? The gas vapors.
She tries to blow it out.
Yeah, that's my favorite. She leans in and tries to blow it out. Then she bangs it on the ground and then walks off. Now,
No, I thought she was making
right there, incidentally, what doesn't happen?
She doesn't get burned.
Okay, she doesn't get burned, at least not severely, and the car doesn't explode, right? That's one of those Hollywood myths. Your car will not explode. Your gas tank will not explode. Good, because it's only the fumes of the gasoline that are highly combustible that explode. The gas will burn. It will absolutely sustain a flame, but it won't explode. It's just gas vapors. Well, no, you still want to get away, right? Because if the tank ruptured and the fumes escaped, then that could be a real problem. But it's not going to do like in Hollywood
So then
style.
why is it like your car has to be off when you get down? Why is that?
For the same reason that they tell you not to use your cell phone and anything else. Basically, they're trying to avoid anything that would have any kind of spark.
Oh, okay.
And yeah. So there we go.
Well, I love